so you know me already. I'm Jordi, and I would like to share with you linguistic tricks to speed up and make, let's say, feasible some specific types of linguistic analysis, as we will see, mostly having to do with document classification. And the title of the talk is this one, and the most important words in this title are unsupervised and obviously linguistic tricks, which are going to be the focus of the talk. I suppose I don't have to define social media. This is Twitter, Facebook, things like that, you know, like ephemeral content, user-generated content. And that's it. So I think that's all the background you need. Let's start. Assumptions. The assumptions for this research are pretty straightforward. Given a big collection of unseen documents and no minor notation whatsoever, we want the system to, and we will see what we want the system to. But before this is really important, because of what I was saying before. Annotating data with manual labor is really expensive, takes a long time, and usually, apart from being really boring, can lead to inconsistencies because human annotators make mistakes. So, as much as possible, you want to avoid that. That's the first good reason not to use annotated data and try to use unsupervised learning. The other good reason is that usually we don't have information. If you consider any time-critical application, you don't have time to annotate data and teach the system what it's supposed to learn, because you need to tell the system, and you still don't know. So we need to be able to make a system that can learn what's relevant from the data on its own, okay? So we don't want anybody telling the system what it's supposed to learn. We want the system to learn what's relevant, with some general definition of relevant that we will see, but we want the system to figure that out by itself, on its own. And the most important reason why we want to avoid using annotated data is because it's the year 2012. I mean, we can't be still telling our systems what they're supposed to learn. They must be able to learn it by themselves. It's like 2012, we're still like this, like nothing changed. So, objectives, what we want the system to be able to do. We want it to automatically identify all the relevant topics. And by topics, I don't mean trending topics as in Twitter, like one word, this word, one hashtag. No, I mean a topic, a conversation, a unity of meaning, more than one word, probably 2, 3. We will see that 3 is usually a good number. But we want that the system doesn't just focus on specific entities, but on whole stories, something which is meaningful to people, something that can be useful to classify a big collection of data in suitable, meaningful categories with, again, no supervision. Out of those topics, we're going to isolate the most relevant ones, the most frequent, and the ones that say the most. And we're going to classify those documents based on those categories. And we want to be able to be happy with the results. That's important, because if the system does all the 3, but then the results are not good, then we may as well go ski or something. So, the question we want to answer is what's in the data, and we don't know. So we'll have to make a guess. And another of the assumptions of this research is that words carry meaning, and therefore if a text has meaning, that meaning can be traced back to its words and nothing else. No annotation, just the statistics, just the words and their frequency, their occurrences. That's all we need, or that's all we want to use. So, definition of guess. I know it's a not technical term, but in this presentation it will be a technical term. A guess for us would be, in any sentence, any combination of any 3 words, we will see why 3, unique words, regardless of distance, and regardless of the sequential order, during generation, we will see what this means, but stored always in alphabetical order to make sure the results are consistent and be able to aggregate them. We will see how this works. So that this is true. For those of you who speak Python, this has to be true, okay? So string 1, string 2, string 3 sorted alphabetically is the same as this one. Why do we need this, and why 3? Well, let's consider tweets. This is just a small sample of tweets collected for the keyword Obama shortly after the election. And probably the words in bold are the words that we want that the system learns to use as features of the classification. We want the system to find out somehow that Obama is important here, and so are campaign and stuff. Because it seems that those words, and just those 3 words, would allow us to classify this whole data set, okay? So, probably 3 is the right number, because 2 would be just too little. For most applications, it is. 4 would be just too many. It's going to be difficult to find the exact 4 words all the time in sentences. I think 3 is the right number. Why do I think that? Well, because if you think of language, the whole point of language is basically unifying nouns. In a we deal with sentences. In a sentence is basically an excuse to combine one noun with another noun, which is basically a subject and a direct object through a verb. That's a 3rd word. There is this trend that languages usually use these 3 elements in every sentence. So we're going to assume that that's okay, that we don't need more than 3 elements because it seems the languages can work it out with just 3 elements. So let's assume that that's okay. And let's make a system that finds those 3 elements in all the sentences. Before we get to this. So, because we are going to guess, because we don't know what's in the data yet, we want to find out, we have just to make all the guesses that we can. As many hypotheses as possible, make all the inferences, and then aggregate the results and see what ones are the most frequent. But if we do that, if we make all the possible combinations, we're going to have a problem with combinatorics because there are just too many. I mean, if you combine every word in a sentence with every other word in a sentence, you get a lot of possibilities, particularly for big texts. Solutions to that. This is where the tricks will start. Okay, probably I don't have to explain this. I mean, I assume that you all know that, well, let's not assume anything. So, given this set, 4 items, okay, and given this piece of code that basically says that for x, this is just to find all the pairs, all the possible pairs given this sentence, this set. So, for x, and for each y, whenever they're different, we add the pair. And for 4 elements, for a set of 4 elements, we get 12 combinations. This is math, basic, no argument here. So what happens if we turn this 4-element set into 2 2-element sets? I mean, most of you already know, same algorithm as before, we get just a length 2 set. So even if we're using 2 sets, 2 times 2, it's still 4. And the most important part, 4 is of course less than 12. So if we, I know, well, I don't assume anything. So we want as much as possible to use this because the fewer the combinations, the easiest it's going to be to make all the inferences. And we want to make all the inferences because we still don't know what's in the text and we want to find out. So we have to guess and we have to shorten as much as possible the units of analysis. How do we do that? Well, what I just said. Oh yeah, and the other way, besides shortening the unit of analysis, we want each unit of analysis to have as few items as possible, okay? Because that also will speed up and decrease the number of possible combinations. And we want to decrease the number of possible combinations. So, in many applications of computational linguistics and information retrieval, they still treat documents as a whole, as a bag of words. Like they just take all the words in the document and that's it. That's their search space. If we do that and try to make all the combinations, we will be dead. So we need shorter units of analysis as per what we have just seen. So we are merely going to cut every sentence for at each punctuation mark. We're going to split in each period, in its question mark and its exclamation mark. We're going to get the sentences, and that's the basic unit of analysis we're going to use. Not the whole document, that's too many combinations, just smaller sentences, okay? First trick. Second trick. We want to decrease the number of items in each sentence. What are we going to do? Consider this text. This is a natural language text with all the prepositions, all the articles, and all the junk. All the junk that we don't need for understanding the general meaning of this text. So, we don't need that to classify this text. That's redundant in this point. We need that for deep linguistic analysis, but we don't want to do that. We just want the general meaning. So, we don't need that. Let's remove that. So many less combinations. But we don't need those words either because they don't mean anything. 10,000 of course passes. Well, yes, of course, it means something, but it doesn't tell us what this text is about. Let's get rid of those as well. And some weird words that are also not that frequent, let's get rid of those as well. Northern glimpse, darkness, yeah, whatever. So we're left with this. Now, this is the meaning of this text. Tourists, astronomers gather Australia solar eclipse. You don't need any more words to understand what this news is about. You know it's about the solar eclipse in Australia and gather tourists and astronomers. That's all we need to know. So, how do we get to this point? Well, it's really easy. Oh, these are good examples now. Okay, forget that I have no time for this probably. So, in order to clean the text from all the junk, we're going to just remove, for those of you who speak Python again, all the words which are stop words. What are stop words? Stop words are words such as the, of, from, prepositions, articles, and things that don't contribute meaning to the text. And the second thing we're going to do is remove all the words that don't have a frequency above some given threshold. In this case, maybe once, twice, 3 times. Anything that appears fewer than this threshold is going to be removed as well because it's noise. And that way we get a more manageable size over which we can calculate all the possible combinations. Okay? And I probably don't have time to explain this. 1 second. Any idea what engrams are? Yeah, everybody? Yeah? Okay, so what's the problem with engrams in this particular case? I'm not going to explain this, you know, they're great, but engrams, which are great for everything having to do with fluency in sentences or language, are not great in the example that we were seeing before, because here we're interested in pairing, connecting this word and this word and this word, for instance. And as you can see, these are not engrams, because one engram would be President Obama cries. That would be an engram, because they have to be strictly contiguous. But that's not the best. I mean, we want these long-distance relationships, because for many things, it's going to be more realistic. Why it's more realistic? Because consider Russian. In Russian, the elements of the sentence, the subject and the object can move, and the relevant words can be in some places different than you would expect. I mean, not extremely adjacent to each other, but at any point. English is much less so, because you usually have subject, verb, object, and that's it. Okay, nice, but I mean, English. So we need a formalism that captures this type of long-distance relationships and in any order. So we can't use engrams. More examples of not engrams either are these ones. Again, these are labels learned automatically by the system over data shortly collected after Obama's re-election, okay? And as you can see, this all makes sense. I mean, if you follow the news in the US, these were all the main news stories of during the election and after the election. Like, you'll see the system got all of them. And it learned this with no annotation. I had to tell nothing to the system. Just based on the statistics and combining all the possible words in its sentence, it extracted these 3 item sets, which makes sense to us as humans. So any classification that fits these labels is going to be good for us. We're going to be able to make sense of it. So we want to get to this point, but we can't use engrams because they're too strict. So this is the big trick. We initialize an empty list, and for each word in the sentence, we're going to combine that word with every other 2 words, distinct words in any order. Then we're going to sort them. We're going to just underscore them to treat them as a string, and we're going to add them to inferences initialized before. So we're going to keep doing this, creating all the possible 3-word pairs from a sentence, okay? 3-word sets, not pairs, of course. So, once we have the 3-word sets, we count everything, as empiricists usually do. And the results I will be able to present you right now. Before some quickly explanation of the dataset. So as I was mentioning before, we're going to take a look at tweets extracted from Twitter's web search API. 1 day worth of tweets for the web search is not the full data set for Twitter. And we're going to see what results we get for the keyword Obama. Clean, but still very noisy. We'll see, I mean, when you look at examples, you'll see that it's the case. Totaling 110,000 inputs, tweets approximately, this many bytes, so 15 megabytes. Not a lot of data, but quite a lot of text. I mean, it's a respectable amount of text. The results that you're going to see were generated by the system in 7 minutes. Just keep that in mind. If we can, we're also going to take a look. Yeah, actually, I have to make sure that we do. We're going to take a look at the classification the system was able to find for an email corpus. Emails obtained by a subscription to an email distribution list, cleaned from the email language markup or something like that, not as noisy as the tweets. And the most important thing, the emails are classified manually. These are using a set of known tags that appear on the email subjects. So this data is going to allow us to measure the precision and the recall of the system, which is always something you want to do to ensure the system works well. So we're going to see how well our system works based on this data. And keep these numbers in mind. This is really important. So in the data set, there are 418 emails with calls for papers for conferences, 260 emails with job offers, and 272 emails of publishers announcing books. Okay? And the third experiment that I don't know if we're going to have time to take a look at is the same as the first one with results for Skyfall, the last James Bond movie. You know, it's a nice topic. And again, you will see, if we get there, you will see the system was able to find, again, the main news stories for that keyword after the release of the movie. So kind of cool. But we will get there if possible. So we switch to the terminal now. You still see this. So where to begin? Let's take a look at Obama results, okay? Because we saw that we had some nice categories. This is the whole index from frequency. So we have 1,017 documents for the first set of tags, okay? And then decreasing number of tweets for each set. And we find like fiscal Obama cliff, you remember this one was in the examples, and Mitt Romney Obama as well, so 904 tweets. Now, we see there appears to be this many tweets which match this query, basically, like that contain these three words. Is this true? And if so, do these three words, when used to classify these documents, point at a conversation, a story, something which is meaningful for a human subject, and that this subject can recognize as a relevant content having to do with a consistent topic? Let's validate, let's take a look. So let's choose the fiscal cliff, for instance, and this is what we get. Can you read it more or less? Not that well? Okay, let's try to do, I think, yes, okay, it should be a bit better, right? So, this is the document index, this is the tweet or part of the tweet, and the fiscal cliff is a problem that happened in the US because they were approaching this moment where, I don't know what's going to happen, some law was going to come into effect and they're going to have economic problems, something like that. So there was a fiscal cliff. Okay. And we see that correctly, all the tweets in this category have to do with this topic. We have President Obama will deliver a statement on the economy, fiscal cliff, but then with a quite different, almost entirely different wording, we have that on Good Morning Washington, in just a few minutes, like some news anchor is announcing something, Obama is said to talk about the fiscal cliff. So Obama, fiscal cliff, but still different wording in the first one. So we don't depend on things like engrams, which are really strict. I mean, you probably wouldn't be able to catch these using engrams because they're different words and different orders, different distances. But with this system, making all the possible inferences or all the words in its sentence, you can capture that. Any distance, any order, that's okay. Different one, Krugman, like this economist, Dear Obama, don't make a fiscal cliff deal. It's again relevant to the topic, but different aspect, different point of view. Like we have the main story, all the related stories, all the different aspects of the story in one single category. The system learned everything on its own. We didn't have to annotate anything. Well, kind of effective. So this is just one example. Let's consider some other examples. Let's take a look at the index again. So I don't know. The second one is important, this one, El de Obama. Those of you who know Spanish know that those are I mean, the article, the preposition in Spanish, and then Obama's name, which means that the system has also been able to find that, oh, all these tweets here with these features are a different thing, like, because they're in Spanish. The system doesn't know it's in Spanish, but it finds that different words correlate with that and just groups that as a different category. It doesn't have to know Spanish. It just finds that it is relevant category, so it just infers one. So we could even perform demographic analysis with this tool. I mean, if there is something to say, the system is going to find it because we have enough data to back it up. So the system just creates a category. That's, I think, very interesting. And we can take a look at some other, out of what you see, any preferences? Just pick one. I mean, which one? This one? Okay. I hope it's not a fluke. So this is what appears. Some other language probably, and some URL. Yeah, so bit.ly, of course, that was a problem.
Retweet? No?
Some of them are going to be retweets, yeah, but that's not the only reason, because if oh yeah, it's in the categories, yeah, right. In this case, it took the retweet label. Yep. That's correct. So that's part of the information that the system considered. And so there is also the bit.ly URL, and then probably here we have all the retweets for all the bit.ly URLs having to do with Obama. So that's also useful information. You can see how many users or what's the traffic that bit.ly links collected for this data set in the given time. So it's another piece of valuable information you want to perform that kind of analysis. Any other examples?
Obama fired N-word.
Okay. Which one? 300? Okay. N-word. Oh, that's the nigger word, probably. Yeah. Okay. Yeah, we'll see. Yeah, that's correct. So you see, North Carolina woman fired for nigger word, Obama reference on Facebook. That's it. Another story. All the retweets and all the different variations for that story, like in the news, big deal, all the possible combinations. And yeah, exactly. And actually, hoping he was assassinated even. I mean, this is kind of like some crazy stuff here. But the system found out because obviously this is a big deal, lots of tweets about it. The system has it really easy to find those tweets, group them together, and produce a category. No annotation, no supervision needed. You can query the system every morning, no necessary input from your part. The system is going to tell you everything which is important. Cool. So, now, more proper evaluation. The emails dataset. So, if you remember the numbers, these were the numbers, okay? 418 conference calls for papers, 262 book announcements, and 260 job announcements. Let's see if we can find any category that matches these numbers as close as possible. So, okay, the closest that we get to 418 is this 403. Not bad. And for jobs was, for jobs, how much it was for jobs? How much it was? Okay, 260. Oh, that's the one I like. Because we have a 260 here, which is specialty ranking areas. Does this sound familiar? Yeah. Does this sound like it could have to do with jobs? So let's take a look at 260. We have two false positives. The first three. Okay, three. But then you see jobs. The tag that was used in the email to classify, in the email subject to classify all the jobs announcements. And it goes till the end. Jobs. So, and support, of course, it's a call for a job as an intern. So also that one. Even though in this case the email subject is different. So the system here is even correcting the manual notation. That's because behind this there are like the careful and really well-meaning people that produce the linguist list. And I mean, this is correct. Actually, support is a type of job. But the system has been able to identify that, okay, this could also be classified under these other labels, so maybe it's not a big deal, and that's correct. So in this case, when the authors of the distribution list decided to classify this as a different tag, probably makes sense in their scheme, but still, it's good that the system finds out the commonality.
So no subject wasn't in the data?
No, of course, yeah. If it was, you would find it as a feature. And as you can see, there is no jobs here. So that would be it, exactly. And if you remember, we had books as well, which I think we can reconstruct. It's very easy. So it was 272. We have 274, which would be 100% precision, 100% recall, and books, a journey through knowledge, all the titles, blah, 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 all the authors, correct. So what happens with the 2 extra that we got? Because we have 274, and there are 272 in according to the email subjects, okay? So if we go to the end of the list, we find these 2, FYI, okay, which, in fact, is a fake publication that a researcher submits as, you know, it announces it as a publication, as an article, because he always announces it as some kind of magazine. So it makes sense, again, that the system has classified this as a book announcement. So we got all the ones that were correct according to the manual notation without using that manual notation, and even 2 that matched the general meaning of that category.
By
So
the way, it was also one conference, I guess. Confs.
yeah, oh yeah, that's correct, yeah, exactly. Yeah, that's false negative, positive, yeah, that's correct. Well, still 90-something precision, but, you know, taking into account that we have fed the system no human input, I think it's quite remarkable. And I think I have 3 minutes, so we had the calls. Did we take a look at the calls? I don't think so. So the calls is one. Calls. Out of 418, the system got 403. So there were 15 missing ones. For some reason, the description didn't match this one. We have to deal with that, but it's, I mean, not such a big deal. It's not a terrible loss in recall, so I think it's very reasonable. And we got most of them. And again, it's really relevant. Like, all of them have to do with goals for conferences. And the reason why this is the tag is because in the fields for the conference, one is like the description of the area, and they all have to do with linguistic information. So the system found that, grouped the words together, and again created a category. So I think the system kind of shows it's really smart. And again, consider that we are not using any kind of human annotation. So the fact that we can achieve this level of precision, which is really remarkable, with no prior knowledge at all, I think it's kind of a big deal in the industry. I think, at least I'm not familiar with anybody else doing this kind of thing. And finally, we can take a look, quick look, to the, to the Skyfall results, the movie, and we will see that it makes sense again. James Bond Skyfall, of course, that's the most frequent one. All the tweets have to do with this. Then, oh, this is a one in another language, so don't pay attention to that. Again, retweets. For some reason, maybe it's a bot or something, because we get the retweet and then different language tweets, kind of Twitter problem probably. But after that, we have the James Bond box, which refers to the box office, so we can take a look at that. And we see that, in fact, it says how James Bond soars to box office record, different wording. The first one, Skyfall fetches 55 million pounds in new US box office, whatever. So all different combinations, all different linguistic variations, all in one single category based on 3 words. Really interesting, and again, probably the most interesting part for me is that, if you consider just, I mean, see how quickly this drops. So out of the total of tweets, 1,400 were found to have this tag, which is like normal, big deal. That's the main subject of the main topic of all the tweets. But then, again, we have all the main stories, like the car, which is a big deal in James Bond movies, like the car that James Bond drives. That's something important, people are usually curious and want to see the car, it's really advanced, whatever. It's one of the main topics, again. Daniel Craig as Bond, it's also one of the topics where there was this discussion whether he was the best James Bond ever, or not yet, or yes. It's, again, one of the news stories. So basically, taking a look at the top 10, we can extract automatically, no human intervention, the most important news stories for any given keyword that we want in the period. These results were really fast, under 5 minutes, I think maybe 1-2 minutes. And I think it's quite interesting. And I think I've been speaking for 30 minutes. So if you have any questions, anything you want to know, see more examples, whatever, just feel free to ask. Yes?
I have a question. I'm very interested in the system you presented. So my question is, the main task of the system, as I understand, is classification, right?
Yes.
You find different classes.
Yes.
Although I think it's better to say clusterization, isn't it?
In some way, yes, yeah, absolutely, yeah.
Okay. Say you have 300 posts, or tweets that match the keywords of Obama-fied N-word, as far as we saw.
Yes.
And then say you have another 300 tweets that say our president sacked black woman, like something like that.
Okay.
So this is actually the same topic, so the same class.
Yeah.
But in which way are you going to unite them?
Right. I wish I could tell. Right now, the system figures it out. I don't have to tell him.
Excuse me, there is one possibility. Maybe another word will be common for both cases. First one.
Exactly. If there were common words, since those will be more frequent, those will be the features of the system, because the system just chooses the features based on frequency. So if there is some better three-word item that clusters more words than any of the other two, that's going to be preferred always over the other two. So if there was some commonality, if there was some other set of 3 words that explain both data sets, they will be clustered that way. Yeah. So if it's in the text, the system is going to find it. That's the truth. Yeah.
I guess it's just a very easy approach to combining this text, just based. So if the sets of documents are similar, you can just
some intersection.
For example,
Yeah.
intersection is more than some percent.
Mhm.
So we can say that these both topics describe one
Story.
One story, because probably one set of document is related to only one story. But if you have only one story in the document, then it's trying to tell.
That's why you want to use sentences rather than documents. Because
What about using limited dictionaries?
of course, that
Like ontology.
yeah, that should improve the results. I mean, if the ontology is well built, of course, it should improve the results. Yeah, absolutely.
Few of them.
Yeah, that's an option. I mean, this is extremely basic, actually, and also bear in mind that this is linguist code. It's not programmer code. So based on previous experience, I know that any decent programmer would be able to speed up this a lot, and on the other side, any competent linguist will be able to devise even more clever tricks to use so that the clustering can be expanded, enhanced, and increase coverage and precision. Absolutely. Yeah, I think there is a lot of work to do yet. Again, basic stuff, but what I've described is basically the main idea behind the approach. So I think it's really simple, and given how simple it is, the kind of results that we're getting, it's quite encouraging as well. Any more questions?
So can you please clarify once again? So firstly, you generate all possible 3 sets of terms, and then you just look all the tweets and counts each tweet which has these 3 words.
Yes.
Last one just
That's all I'm doing. It's sadly easy and basic. Yes, that's correct. Yeah. That's all there is. You need to clean the text, I mean, because you want it to be computationally feasible, so you have to remove as many junk, stop words, low frequency words as possible, because you don't want to make those hypotheses. But after you've cleaned the text enough and you only have the most relevant, most semantically important terms, it's just a matter of combining and aggregating the results and counting, just counting. Yeah, that's correct. Yeah, sorry.
Did you consider stemming words before?
I haven't done it. It would be another improvement. Exactly. Yeah. It's this basic. I'm sorry, but it's this basic. I mean, we get these results. Yeah.
Are you removing words that are less frequent in English or in our text?
In this case, in our text. but you could use any other data set to estimate the frequency and then rule out those words. It's open to the researcher. Yep. Yes?
Okay, after removing stop words, you remove some common nouns, adjectives, adverbs, as far as I understand. How do you define which nouns are frequently used? So do you find the frequency in the text that you're training the data on?
That's probably a question for another talk, because that has to do with the work I've been doing in this company and my previous one, actually. There are ways, but basically the basic idea, like the simplest way to put it is, as I pointed out, using a stop word list to remove the most frequent ones, and using some threshold to remove the least frequent ones. And then there is some area where that the stop list word usually, the stop word list doesn't usually cover, which includes words such as tens, thousands, and the kind of thing that you should try to somehow recreate. We have our own way of doing it, but I could explain, but it would take long. But if you're really, really, really interested, I guess we can talk, discuss it, or it could be the topic for another talk. But yeah.
После мити будет пицца. Да, we will have pizza after.
Okay, so thanks a lot for your attention. I think we are free. I mean, yeah, we can next speaker, right? Yeah.